In lecture 5, we are going to study average energy of electrons, and we will derive the relation between average energy and Fermi energy. Now, in the last lecture, we have studied the distribution of electrons for semiconductor at temperature equal to 0 Kelvin and temperature greater than 0 Kelvin. And we used Fermi distribution function to explain the curve, probability curve for the semiconductor at T equal to 0 Kelvin and T greater than 0 Kelvin. Now, in this lecture, we are going to derive the relation between the number of electrons and Fermi energy. Furthermore, we are also going to derive relation between average energy of electrons with Fermi energy. Now, on your screen, you have the distribution function formula for electrons, which we have studied in the previous lecture. So the distribution function formula is Ni by Gi 1 by e to the power of alpha plus beta ei plus 1. Now, if I substitute the value of alpha and beta, I get the distribution function for Fermi statistics as 1 by e to the power of E minus Ef by kT plus 1. So, using the distribution function formula, we are going to calculate the relation between the total number of electrons at T equal to 0 Kelvin. Now, from here, from this equation, I can write that number of electrons as a function of energy is equal to Fe into G. F is the distribution function and G is the number of quantum states. So what I did, I just cross multiplied this. Now, going back to the curve that we discussed in lecture 4, that the y-axis is probability, x-axis is energy, and when the semiconductor is kept at 0 Kelvin, physically it behaves as an insulator, and you have all the energy levels in the valence band is full, so it shows the probability 1, and all the energy levels in the conduction band is empty, so it shows the probability 0. So I need this concept to derive the number of electrons at 0 Kelvin present in semiconductor. So starting from here, N is equal to F into G. Okay, so I'm going to calculate the total number of electrons. So what I'm going to do, I'm going to integrate from 0 to infinity on both sides to calculate the total number of electrons. So what I did, if I calculate or integrate from 0 to infinity, the left hand side will give me the total number of electrons, because I'm going to calculate for every energy level the number of electrons. So I'm going to count and integrate, and finally on the left hand side I'm going to get the total number of electrons, which I name it as capital N. Now, in this integration I mentioned 0 to EF, but if I start from 0 to infinity, which means on the x-axis the energy is from 0 and it goes to infinity. So what I did, I have taken a limit from 0 to EF and EF to infinity. Okay, so in this part of this calculation, why did I take 0 to EF? Because from EF to infinity, the Fe value or the number of electrons in the conduction band is 0. That means no electrons will be present here, or in other words, I can say that the Fe value in this part of the graph is 0. So if I integrate from 0 to infinity on both sides and then break the limit from 0 to EF and EF to infinity, so from 0 to EF you will get this value. But if I plus EF to infinity, that part of the integral will be 0 because Fe value is 0. That is written here. So finally, if I repeat once again, if I integrate from both sides 0 to infinity, the left hand side will give me the total number of electrons, which I write down as N, and the right hand side I break the limit into 0 to EF and EF to infinity. From 0 to EF, the number of electrons is present from 0 to EF because all the electrons are present in the valence band, and from EF to infinity the Fe value is 0, so the second part of the integration becomes 0. So I'm left only with this part, 0 to EF Fe into GE d. Now if I ask you from the graph that what is the value of Fe from 0 to EF, from 0 to EF the value of Fe is 1, and from EF to infinity the value of Fe is 0, probability is 0. So the second part of the integration becomes 0 and you are left only for 0 to EF. So finally I get the left hand side as N, capital N, which means the total number of electrons, and the right hand side I am left with the integration 0 to EF GED because Fe value is 1 from the graph. So I go further in calculation. So I know that GED, this number of quantum state as a function of energy, we have derived this relation from the lecture of phase space. If you remember, we have derived this from the phase space definition when we had the number of quantum state as a function of momentum. So from momentum we have transformed this into energy. So I'm not deriving again this part. So I will use this GED in this equation. I will substitute the value of GED here. So if I substitute the value of GED, it looks like this. The capital N is equal to 8 root 2 pi V m to the power of 3 by 2 by h cube. All these are constant, so they go outside the integration, and 0 to EF limit e to the power of half t. So I have to do this integration. What will be the value of the integration after I substitute the limit? I get EF to the power of 3 by 2 divided by 3 by 2. So I get it in this way. So capital N is equal to, if I solve this integration and substitute the limit, I have EF 3 by 2 and the denominator I have 3 by 2. That 3 by 2 goes up, that means 2 by 3 it comes, and 2 multiplied by 8 you get 16 root 2 pi V m 3 by 2, and the denominator you get 3h cube, and you get EF to the power of 3 by 2. So this is the relation between the Fermi energy and the total number of electrons. So if you have the value of, for a semiconductor, if you have the value of Fermi energy, you can calculate the total number of electrons. Now this equation can also be written in this form. How do you write it? If you multiply the left hand side and right hand side of this equation with the power of 2/3, so what will happen if you multiply both the hand side of the equation with the power of 2/3, then EF becomes power of 1. And if you take Fermi energy EF to one side, you get this relation. So both the equations are correct. Either you write it in this form, N is equal to some constant EF to the power of 3, or you can write down as EF to the power of 8 square by 8m 3n by pi v 2/3. H is Planck's constant, m is the mass of electron, n is the total number of electrons, and v is the volume. Now we come to the mean internal energy or average energy. So before I start the derivation, basically what is our motto? Our motto is to calculate or find out the relation between average energy and the Fermi energy. So before I start the derivation, let me explain you or define average energy or mean internal energy. So what is the definition of average energy or mean internal energy? It shows that E bar, which is called the mean internal energy or average energy, is equal to 1 by capital N. Capital N stands for total number of electrons, from 0 to infinity E n function of ED. So what does this n function of means? It means not the total number of electrons. It means the number of electrons in that energy level. So in this example, what is the number of electrons in this energy level E1? I will have 3. What is the number of electrons in E2 energy level? 2. So what I'm going to do, 1 by n. So what is the total number of electrons? 3, 2, 5, 6, 7. So what I'm going to do, this n is multiplied n is the number of electrons present in that energy level multiplied by the value of that energy, and this will carry on from 0 to infinity. So this is the definition of mean internal energy. So if I go further with the calculation, then if I break the left hand side, I have the mean internal energy, and this integration I break into 0 to EF and EF to infinity. From this graph you can understand that the energy on the x-axis 0 to infinity, that I break up into 0 to EF and EF to infinity. So how does it look like? It looks like this: E bar 1 by n 0 to EF, EF to infinity. Now you may ask me that where does this n function of E, that is number of electrons for that particular energy, go? I wrote it down as n is equal to F into G. If you cross multiply this, you get this. So for every n in the integration, I substitute as F into G, and I break the limit of the integration from 0 to EF, EF to infinity. Now if you look into the graph again, you will find that from 0 to EF, the value of Fe is 1. So I can substitute the value of Fe 1 here, and from EF to infinity, from here to here, EF to infinity, the value of Fe on the x-axis is your Fe is 0. So here I will substitute 0. If I substitute 0 here, this second integration on right hand side vanishes. Okay. So this part of the integration vanishes, and then this part of the integration, this value of Fe is 1, because 0 to EF the value of Fe is 1. So what I have E bar is equal to 1 by n. N is the total number of electrons. 0 to EF, E into G, because Fe becomes 1, D. So again I will use the value of GD, which has been discussed in the lecture of phase space. I will take this value of G and substitute here, and after substituting I will take all the terms to the outside the integration because they are constant, and I will integrate as a function of energy. So what I will get, if I substitute this, take this, call the terms outside the integration and do the integration as a function of energy, here it is e to the power of 3 by 2, and the limit is 0 to EF. So I will get the value as EF to the power of 5 by 2 divided by 5 by 2, and 5 by 2 goes up as 2 by 5. So I get it in this way: E bar is equal to 4 pi Vn 2m by h cube to the power of 3 by 2 2 by 5 EF 5 by 2. So I have done this integration and substituted here. Furthermore, what I am doing, already I have derived the relation between Fermi energy and the total number of electrons few slides back. So I will take help of this value and substitute here. How do I substitute? I break this value of EF to the power of 5 by 2 as EF to the power of 3 by 2 into EF. So if I break this as EF 3 by 2 into EF, and then furthermore if I substitute the value of EF here only, then what I'm going to get? I'm going to get E bar is equal to 3 by 5 EF, because all the other terms after substituting the value of EF to the power of 3 by 2 all will get cancelled, and I'm left with E bar is equal to 3 by 5 EF. So this is the relation between mean internal energy or average energy, denoted as E bar, is equal to 3 by 5 Fermi energy. So we come to numerical. So calculate the Fermi energy for metallic silver, assuming each atom of silver contains a single free electron. So for every atom I have one electron. The density of the silver is given and atomic weight is given. So what I have to calculate? I have to calculate the Fermi energy. We have derived this relation EF is equal to h square by 8m 3n by pi v 2/3 in few slides back. The relation between the total number of electrons and Fermi energy, where h is Planck's constant, m is mass of the electron, n is the total number of electrons, and v is the volume. Now what I'm going to do, I'm going to first take this n, total number of electrons, divided by the volume as number density and denoted as small n. Because I will have to express this from this numerical, I have to express as number density, not as number. So what I have done, the small n, that is called the number density, I have taken the Avogadro number because atomic weight is given. So I converted this number of silver atoms, that is the 1 mole or Avogadro number, divided by the atomic mass, multiplied by the density, will give me the number density, that means number of electrons per unit volume. And I express this in terms of SI unit, that is per meter cube. It was per centimeter cube, but expressed in, for my calculation, I expressed as per meter cube. So I have the number density small n. So I will use this formula. EF is equal to h square by 8m 3n by pi, because capital N by phi I have converted to as number density. And then I substitute the value of n. Planck's constant is known to me, 6.6 10 raised to minus 34. Mass of electron is 9.1 10 raised to minus 31, and the pi value is 3.14. And as I have taken this as SI unit, so I will get the energy as joule. But generally, when you talk about semiconductor, you express in terms of electron volt. To convert this joule into electron volt, you have to divide this by 1.6 10 raised to minus 19, and after calculation, you get 5.5 electron volt. So questions from this part of the lecture? We have derived the relation between average energy and Fermi energy. That is a very important question. E bar, mean internal energy, is equal to 3 by 5 Fermi energy. You have another numerical, calculate the average energy if the Fermi energy at thermal equilibrium is 15 electron volt. So Fermi energy is given, EF is given. You have to calculate the average energy. So E bar is the average energy is equal to 3 by 5 Fermi energy. So if you substitute the value of Fermi energy, you will get the average energy. Second question, derive the relation between number density of electrons at temperature T equal to 0 Kelvin with Fermi energy. So you already have, we have derived few slides back in this lecture, that relation between Fermi energy and total number of electron as EF is equal to h square by 8m into 3n by pi v, the whole thing to the power of 2/3. So capital N by V is your number of electrons per unit volume. So that is called the number density. So if you derive that relation and make that N by V as number density, you arrive to this question. So we come to the end of lecture 5. Hope you liked it, and thank you very much.